I guess now you see it again.
Yeah. Yes. And we are looking forward to the presentation on optimal control of partially observed diffusion processes. Please go ahead.
All right. Yeah, thank you. I hope you can hear me clearly. If not, I have to tune up the microphone. Anyway.
No, I think it's good.
Okay, thanks for being with you. I hope next time I will be able to be there in person. I mean, it's always a bit tricky because it's during term time for us. But anyway, one day will work out. What I'm going to talk about is closely related to what Raul was talking about earlier today. Except the main difference is going to be that I will stay time continuous also when it comes to observations, and maybe pushing a slightly different direction. Anyway, the problem is pretty much as stated in Raul's talk. So you have a diffusion process which is controlled. The control is U. And contrary to standard optimal control problems, the initial condition is uncertain. And then you have a cost. Well, that's standard. So in order to control this whole thing, also in terms of uncertainty, you need some data. And I assume it's sort of partially and noisy. And as I said, it's different in difference to what Raul talked about earlier. It's time continuous. So Y is continuous in time, and it's subject to Brownian noise. And H is the forward operator that links the model states with the data. Now, again, as said earlier, the thing is that the control then will no longer be state dependent, but it depends actually on the filtering distribution, which mathematically is extremely beautiful. It's just lifting up everything to the states of probability measures. Computationally, of course, it's a huge headache. And it's I think, largely open problem how to do this efficiently. Because you have to do filtering or data assimilation simultaneously while also doing control. Now, there is a famous case where it is possible to do when everything is linear and Gaussian. Then there's a separation principle saying that you can do both problems independently, so to speak. And you can compute the optimal control pretending that you actually know where you are. And then the control is based on the expected value under the filtering distribution. Anyway, so we would like to go a little bit further than that. And this is what this talk is all about. Now, computationally, a very efficient method to solve infinite horizon problems like of that type, this case discounted with a discount factor, is to actually do a control over a finite time window, which is moving along as you try to solve the optimal control problem. And it's called receding horizon control, or in engineering, it's called model predictive control. And if it's nonlinear, then it's nonlinear model predictive control. So in engineering, this has become a very popular method to do standard control or to address standard control problems. So effectively, you dealing with a finite window, you start at time t, and that's moving. And then you go tau units of time forward, over which you compute the control, minimizing the cost function as is stated there. And one of the crucial things, which I'm not going to talk about, is that at the end of this interval tau, there's a cost function f now, the final cost over that window. And how to choose is there's a lot of, I mean, that's very crucial to make the method work. And it should, of course, be related to the infinite horizon optimal control problem that you're trying to solve. But anyway, let's just assume that we have that. So now we have to solve that control problem, and we have to solve it online. So this is constantly done now. It's not offline, but it's really online that you're constantly computing these control laws. And then the idea is that you do this and use the control that you get over a shorter interval, all right? Because computationally, of course, you have to have the control somehow to apply it while actually computing it. So there's a bit of a timing issue. Again, we basically kind of rock this under the carpet. But the idea is you have one window where you compute the control online, and then there's a shorter for which you're applying this, and then everything moves parallel to each other. So anyway, so that's a hugely successful and implementable method and used widely in engineering. And so we now want to extend this when you actually don't know where you are currently with absolute certainty. So you have to solve the filtering problem. So essentially, we want to combine model predictive control with data assimilation or filtering. So in order to do this, let me briefly also recall one of the most popular methods these days to perform the filtering or address or approximate the filtering problem, which is the Kalman filter, ensemble Kalman filter actually, which is the extension of the famous Kalman filter from the 60s for linear systems to nonlinear systems, pioneered in the geosciences and now widely used in many fields. And it's a very intriguing method. It's an approximation to the Kushner-Stratonovich equation, but it's a often very robust and reliable approximation. And the beauty of it is that it augments the original model. So let's assume for a moment you know actually what the control is. And the data comes in, and the real data is Y dagger. That's something you really observe. And then the Kalman filter in continuous time takes the difference between increments in the real data with data that your model is generating. So this is a forward model that we assumed for the data, but now we are using this to simulate data from the trajectories that our dynamical system is, or SDE is producing. And this is called the innovation. And it's slightly different from the innovation that you have in Kushner-Stratonovich, but it's still, you see, it's the difference between what you observe and what your model thinks it should be. And then it's moderated by the Kalman gain, which is the covariance matrix of the states versus observations and weighted by the measurement error. So that's now the beauty of it. This is a mean field equation. The mathematics is just really nice. So suddenly you start with an SDE, you have a McKean-Vlasov, or let's say a McKean SDE. Actually, Vlasov is probably not the right name, even though it's often used. It's a McKean SDE now because it depends on the law of the process. And it's now a generalization of the Kalman filter to nonlinear systems. So this can all be nonlinear. H can be nonlinear, everything, and you can use it. And I'm not going to talk about the approximation properties today. That's a whole own subject. So this is when you have an observation. So that's when you actually assimilate data. Now, if you do optimal control for partially observed processes, the main challenge is now that when you solve the control problem, you have to anticipate what kind of information the future observations might deliver to you. And you have to take an expectation of all these possibilities for the future and the information it contains, essentially. So now the beauty of this formulation of the ensemble Kalman filter, or in general, actually, you can also do it with Kushner-Stratonovich, is that you know that the innovation becomes Brownian motion if everything goes well. So even if you don't know anything about the future observations, basically all you need to do is to replace the innovation by Brownian motion. In the mean, right? So in the expected value of what's going to happen in the future. Now here I have, again, made several approximations. So I pulled the expectation value inside here as well, which of course I should not do, but let's do it for now. I could avoid this, but it just gets much more complicated, but it's doable. I mean, I can do it right on this, but it's just so a much nicer formulation if we pull it down to the mean, and I assume that I can pull the mean inside, expectation inside. So basically, the effect of the future observations on these equations in the mean is simply that you add a noise term. Now this term has disappeared, right? Because I've taken expectation. Now this is again, this is acting actually on the mean, the observations, right? So again, I now have a stochastic optimal control problem in the mean. It's just, it comes from a different corner, sir. But basically, this, yeah, it's just another stochastic optimal control problem with this new noise term. Furthermore, another sort of simplification for this talk to make the heads not spinning around here is that I also fix the covariance matrix. So, and that's sort of reasonable because I do this receding horizon thing. And so if the window is on or too long, the covariance uncertainty is not dramatically changing over a window. And so over the time window of the 0 tau or t plus tau window. So it's not an unreasonable, but again, it can be dropped. It's just to keep things easier and not making it too complicated. So in particular, why I chose this, otherwise you would have to deal with another McKean equation essentially. Let's just try to stay simple. So now we can use the machinery of stochastic optimal control, and indeed we could use Pontryagin and forward-backward SDE formulations of Pontryagin and do that, and that would be a solution or an approximation to the filtering polynomial. Now, this comes to a second line of ideas I like to talk about today, is how to avoid forward-backward SDEs. I mean, I know some in the audience, of course, love forward-backward SDEs, but I think deterministic mean field formulation is also quite beautiful. And so that's what has motivated work that I'm currently doing with Manfred Opper. And so this is still very much ongoing, but I think it's so nice that I would like to talk about this here today as well. So let's recall what Pontryagin maximum principle is for deterministic dynamics. So we have a controlled ODE. Then assuming that there's the running cost and there's a cost on the control, then you get this Hamiltonian. So you get what this is essentially a Lagrange multiplier that enforces the dynamics here. P is actually the momentum in Hamiltonian mechanics then. And US is the control. So that's standard Pontryagin. And then from there, you first, let's say, in this context, you minimize or maximize Hamiltonian with respect to the control. And then you get this control term, which involves the Lagrange multiplier or the momentum. So you can stuck that into the Hamiltonian, into this, and then you get a reduced Hamiltonian, which now starts looking like classical mechanics with a little tweak that, so you have a potential, which is a running cost. You have a mixed term, which is a bit unusual, but okay. And then you have kinetic energy, which has a potentially position-dependent mass matrix. Now, the thing is that the minus there, so it's actually negative, right? But okay, that's fine because we're actually dealing with a boundary value problem instead of a forward problem. So, but otherwise, if there would be a plus, it would like classical mechanics. But there's a minus, but that's for good reason because we're actually solving boundary value problems, which is stated next here. And again, that's standard, right? And these equations have an initial condition, which I call A, for good reason, which will become immediate in a second. And then the final condition is the momentum is at the end of the interval defined, and it's the gradient of the final cost function. So that's all standard. So how can we extend this to stochastic optimal control problems? So there's now noise being in there. As I said, there's a very well-known and famous forward-backward SDE formulation also in terms of Hamiltonians and etc. I like to strictly stay in a deterministic setting. So the only way out there is, again, to go formally mean field or McKean. Well, McKean has no stochasticity, but it's a mean field formulation. So instead of looking at a 2-point boundary value problem for specific A and then a specific trajectory leading to the final point. Now I allow A to be arbitrary or to come from some initial distribution, which would be the current filtering distribution, let's say. And so A becomes the fluid. I mean, I'm very much thinking of this now like a fluid, right? You have an initial distribution of A's, which are the labels. In fact, X at T is A, right? At T is the initial point in the interval. S is the variable that varies in the receding horizon picture. Now, so the initial conditions are the labels, and they distributed according to some distribution which comes from the filtering problem which we have solved so far. So, but anyway, these are now functions. The x and the momentum are functions. And here's the augmented Hamiltonian. So all this you've seen before. So this is also there if there's no stochasticity, no nothing. Then let me look at this term. So I introduce what I call a gauge variable, which goes back to Dirac and when they looked at Einstein's field equations, and they also arise there and constraint dynamics. So the gauge variable is enforcing a constraint, and the constraint is that I introduce a function phi, which depends on x and is defined via this constraint. So essentially, phi is modeling the momentum. Now we know from Hamilton-Jacobi-Bellman that p actually is a function of x. In fact, it's the gradient of the value functions from Hamilton-Jacobi-Bellman. So this makes total sense, but we now sort of implicitly define it as a constraint. So, and beta again is a Lagrange multiplier, but it has a specific form of a Lagrange multiplier, which will become clear in a second. So I enforce a new function. And the noise is this, right? Once I have this, I can write down what the impact of the noise would be. Again, going back to Hamilton-Jacobi-Bellman and saying, okay, what term should that be? But since I now have a function available, I can differentiate it, and there I go. So that removes the noise from the equations. So it's now a strictly Hamiltonian system, actually a field equation now. It's a field model. And the boundary conditions are that you initialize from the distribution A, and the final conditions are then given by the forward evolving trajectories and evaluated again at the gradient of the cost function at final time. Okay, so you have a beautiful field of boundary motion, and a bit like a fluid, think of it. So the beauty is, if you go through calculations, then it turns out that you can choose beta, right? This gauge variable, you can choose arbitrarily. You can do what you want. It leaves the resulting equation of motion in this new function phi invariant. And so it turns out indeed that, and that was the desired exercise, that if you look at the Hamilton-Jacobi-Bellman equation associated to our control problem, then phi is the gradient of that potential. So it's exactly what it should be, because that's also what p is, right? And so as an outcome, you get not only like when you do the standard Pontryagin maximum principle, you get a open control. Now this is closed loop because you actually have a function of phi here, right? Of course, you have to pay a heavier price because you now have to not solve a 2-point boundary value with exactly 2 points, but you have to have this whole family you solve. But by now I think people got used to solving mean field equations, and so it's maybe not such a pain. Anyway, the benefit is that you can now do stochastic optimal control, and you can also do you get a closed loop control as well. And in practice, of course, what we need to do is to approximate this by an appropriate function class, and then you solve this essentially via regression. So, of course, that sounds familiar. If you do forward-backward SD, you also have to solve a regression problem. So there's no free lunch, of course. But there's no noise anymore. So the trajectory is all very nice and smooth. Okay, anyway, so what are good examples of beta when you got all this liberty to do? So one choice is, of course, you use beta to eliminate the control from your forward problem. So effectively decoupling the boundary value problem into a straightforward problem and some backward problem you have to solve. But you don't have to go forward and backwards. You don't have to do shooting or any of this. You've decoupled the problem. And that's regardless of Gilzanov, right? This doesn't rely on Gilzanov here. So this is completely free decoupling. Yes. So this is one choice. And the second choice would be to say, well, we could maybe do a bit better. So we can remove the noise, the control. But we might, in the receding horizon picture, you often have a pretty good guess what the control could be. I mean, you just take the control from the last window. So you pull that in, but that you know already. So that's something you already have. And then you add this score function, which mimics the noise in the McKean sense. So it mimics the Brownian motion, but now in a deterministic mean field perspective, because the P is appearing here. So you need to know the distribution of the solutions in the forward problem, in the forward SDE problem. But again, the problem is completely decoupled. Of course, you need to do score estimation. Again, score estimation is not such a big deal anymore. I mean, generative modeling is doing it these days all the time. So I think machine learners are not afraid of it. And so this, again, leads to a decoupling, but it's a more meaningful that you guide the forward dynamics where the control problem would lead you anyway. And then you get a backward equation in the momentum. Again, I didn't write it down. I mean, you might imagine that it's getting a bit long. You get quite a few terms there. But again, you're just solving this backwards. I mean, you're solving forward and backwards, and you're done. Okay. So, but it is still, I mean, a bit hairy if you use general function classes, right? So let's, in the spirit of the ensemble Kalman filter, which does sort of linear approximation in an intriguing way, let's say, we're going to try to do the same here as well. So we're going to say we look at linear control laws, which we compute, again, locally over receding horizons. And so you assume them to be linear. And then the beauty of this is the contribution from the diffusion vanishes for linear function because you take second derivatives. So that's out of the window. Beautiful. So we've taken care of this. And then, of course, we have to still do this regression problem. So we have to estimate AS and CS from the trajectories in P and X. So in this case, actually, the forward-backward problem is still coupled the way I wrote it down. And so you end up with this Hamiltonian here. So now you have the standard Hamiltonian as it comes from Pontryagin. And then you have this coupling through this regression problem. So you just add a regression term to the thing. And you write down the equations of motion. Now, because you minimize over ACE and AS and CS, you don't, and these depend on the particle momentum. So it would be horrendous to take derivatives with respect to those things, but you don't because you minimize, so the drop terms all go to zero. So we only have to properly take derivatives in the explicit appearance of X and P. So the equations of motion can be written down. They still, a little bit, but they still, I think, are quite nice actually, because the original control term would have had the P here, which can be highly nonlinear. But here you replace it by the linear thing, which you then will apply anyway in the real control problem. So the forward problem is the proper control problem, essentially. And in the backward dynamics, well, you have the usual things. You have the usual thing from the kinetic energy. And the only new thing that comes in is this term here, which if actually the linear approximation is good, this will be small. Of course, if the linear approximation is not valid, then as for the ensemble Kalman filter, then you get into potential troubles. And the boundary conditions are, again, the filtering distribution up to time t, and then the gradient at final time t plus tau. And how to estimate A and S? I mean, that's standard. These are just covariance matrices, and since you have particles, you just do empirical estimators, and you're done. That's it. So you got your implementation. Right. So now there are basically two things you alternate. So the first thing is you assume you computed the control, then you do a prediction and assimilation cycle with the ensemble Kalman filter using real data. Now we do it over particles. That maybe also makes the whole thing a bit more clear what I talked about earlier. So you compare the real observations with realizations you obtain for each Monte Carlo or particle realization of your process, and the data is being generated this way. So each particle sees its own quotation mark measurement noise, and then its own forward operator, which depends on its own particle location x. And then all particles actually see the same control. That's important, right? The control doesn't know which particle you're applying it to. It's the same control, right? That's important. And the control is obtained this way. Again, I pulled the expectation value inside. So that's the prediction thing. And so that distribution of particles is then the distribution that tells you in the next step, if you do the next control cycle, when you do Pontryagin, how to propagate the particles then to get the optimal control problem. So, and then you alternate this with essentially this formulation here, which you do, you get the particles from this algorithm for given control, and then to compute the future control, you take those particles and you solve this problem. And so you alternate, or it's essentially always simultaneously do both. Computing control, applying the control, doing data simulation, blah, blah, blah. And that's it. Okay, so as I said, these are early days. So I basically started doing this a few months ago. So we did one of the classic examples in the pendulum, where you want to stabilize a pendulum from the lower position to the upright position. In fact, I turned the problem around, so you want to stabilize the lower position. So phi equal to 0 is the one that's unstable in this context. You add a bit of damping, and you add the control in the standard way. And the state space is two-dimensional, so it's a classical example. And but it's the way we implement it is slightly, well, I wouldn't say non-standard, but that we only have observations of the angle, noisy observations. We start from some initial distribution, so you also don't know where exactly you are. And in fact, down there, so I start in the horizontal position, which is actually the position where this is 0. So it's a bit of a challenge actually at that point to decide, if the particles really want to go up in this setting, right? That's where the stable position is, but you want to push them down, but the control is hardly acting in this situation, right? But still it works. And we did this receding horizon thing. So we shift, and tau was 0.2. So the time window, and then the actual control was applied over the half of the window. I used the control, and simultaneously I was, as I said, solving both problems. And so if the noise is 0.25, it recovers it quite nicely. But you see that the data is not, it's sort of okayish. So these fluctuations come from the fact that we don't quite know where we are. And because the system is actually itself sort of intrinsically tries to be unstable, and you're only controlling the mean, you don't controlling the individual particles. So there is uncertainty that's always growing, actually really fast, exponentially. So it's really challenging if you don't observe the full system, and you can only do a mean control, right? Because that's the only thing you can do. Because think of this, if you want to apply this to a real system, you don't have a distribution, anything, you can just give it a control. And that's what, again, makes this problem so challenging, this optimal control under partial observations. So that's not surprising that this is, of course, if you decrease the error by a factor of 10, things get much nicer. And then you have a rather precise understanding where you are. It's still a bit fluctuating, but it's fine. Now, if I were, to be honest, if I were, for example, to double the R here, the thing would fall apart. I'm sorry, there's no magic in life. So maybe if you were to solve the full Kushner-Stratonovich equation plus the full forward-backward SPDEs of stochastic partially observed optimal control, which again gives rise, as I said, just forward-backward SPDEs, then maybe you could push it further, but not with these simple tools I just talked about. Now let me finish. We extended nonlinear model predictive control to partially observed cases. So we have to take the uncertainty in the states into account. We've done this through the Kalman filter, which, as I said, has become hugely popular. And certainly in a lot of engineering applications, it's very reasonable because we assume that we actually know quite well where the system is. For example, if you think about reinforcement learning, the assumption is actually always that you know exactly what the system is reacting to. So here we take a much milder point of view where we say it's partially observed and it's also noisy. So that's the case where reinforcement learning is generally not working at all. Of course, we have a model. We need a model for this, right? Reinforcement learning is model free, right? But this needs a model, and there's no way around it. Now, very much like the separation principle, I boiled it down to a problem where I only need to estimate the mean. That's definitely a limitation. But we get a linear control law, so there's some uncertainty being taken care of, which comes from the uncertainty in the data and the uncertainty in the state. I showed it to you for linear approximations, of course. I mean, if you really want to go deep learning or something, sure, no problem. But you have to, of course, have enough particles, right? So this, by the way, this was run, if I remember correctly, with 20 particles, right? Yeah, so you could go beyond the mean. In fact, the transformer architectures, which are now used in ChatGPT and other things, are perfectly suitable for this because they permutation invariant. Because you want to have an approximation class that doesn't care how you number the ensembles, right? Because that should not matter how you approximate the control law. But again, of course, it's a huge overhead. And it's not clear if you can do this in real time. Well, I did various simplifications here, not only that sigma was assumed to be constant, other things as well. I mean, the covariance matrix I kept fixed for the initial condition. So you can relax quite a few of these things. The formulas get more complicated. And you get more interaction terms potentially and things like this. But I don't think it's a hurdle in principle to restrict it to these cases. And with this, yeah, thank you very much for listening. And if there are any questions, then I'm happy to answer those. And so back to you.
Thank you very much for this very interesting presentation. The floor is open to questions. Let me start with one maybe. So you mentioned this mean field approach instead of the forward-backward BSD, forward-backward stochastic differential equation. I agree. I mean, for me personally, I've always find BSD to be a little bit too complicated. But is there a direct relation between these concepts, or?
Well, I'm not sure how much you're familiar with it's with the generative modeling people doing these days, where they're solving STEs to noise data and then to denoise and going forward backward. I mean, these are forward reverse time STEs, so it's not forward backward, but it's sort of related. Let me try to find the slide here. Yeah, so maybe I can write here. So there's always this sort of thing you can write x dot equal square root of 2 Brownian motion, or you can replace it by minus grad log p t, I mean this being t now, x of t. If you're only interested in the marginal distributions of x and not in any joint distributions, of course they will be, I mean the x's in the first equation are noisy and they're non-smooth. In the second equation, they're very smooth, but the marginal distributions are exactly the same thing. So you can always replace the noise by some deterministic mean field term. The mean field term comes from the fact that P of t is the law of x of t. So you cannot do this pathwise. You can only do it in a mean field sense, or in a yeah. And so so that's the same thing that happens here with forward backward SDEs, that the formulation I gave you or I talked about today is in the same spirit. So the solution paths will be very regular. They satisfy a classical Hamiltonian variational principle. So you can also use all the beauty of numerical schemes that we have for this. I'm not sure how important that is. But one thing remains, that in backward SDE, you basically have to solve some regression problem in the backward case. And here we also have to solve a regression problem essentially in the phi, the function phi I've introduced. So that complexity remains, but it's less noisy in a way. So, and I found that to be useful, but I guess that's debatable. But I would say if nothing else, it's a variance reduction method, right? So it reduces intrinsic noise, which of course in the limit would all average away in all these formulations. But if you do Monte Carlo, it might make a major difference.
Thank you.
There's actually something else, if I may just add, that another beauty, and that's actually some work I also did with Manfred Opper. We did this for gradient flows. I mean, if you have the gradient here of some function, then we know that things equilibrate, right? There's an equilibrium distribution. Now, if you do the SDE version, particles will still wobble around and you never know whether you're really in equilibrium. Now, if you do this for the mean field equation, actually particles will stop moving and then they, roughly speaking, in equilibrium. So stationarity becomes a very, it's a fixed point of this interacting particle system, which is just very beautiful. I mean, you see it. I mean, particles just move from one distribution to another, and then they get stuck, and then okay, that should be the equilibrium distribution, or the approximation to it. So, yeah, sorry.
Thank you. We have a question here.
Can you please comment on the performance of your algorithm in the high-dimensional setting?
Yeah, so that's been a motivation here actually of the whole thing. That's something I have in mind. Of course, the pendulum is two-dimensional. It's not high-dimensional. I totally agree. But the thing is that the Kalman filter, the crucial thing is this covariance matrix you have to estimate. And we know in high dimension that typically doesn't work so well. But then people realize that if you have physical structure, that there's a lot of independence between variables. And so you do truncated covariance estimation, or it's called localization. So meteorologists apply this method to millions of degrees of freedom with believe it or not, 100 ensemble members. So the particle size is 100, and then you run this whole thing over the globe with millions of degrees of freedom, temperature, velocities, and everything. So that's you think this is impossible, and it of course is a bit wacky, but they get meaningful results. I mean, no doubt, and it really realizing that this you don't estimate the whole thing, but it's actually a very sparse object. And so the same here. What I wrote down is essentially the only term that matters is that you have to estimate, again, covariance matrices. It all boils down to expectation, empirical expectation and covariance matrices. So here again, if you want to go to here really high dimensions, you have to use sparsity and structure. But it's the same kind of structure that people use ensemble Kalman filtering. So I'm hopeful that it will be doable. But at this point, I have no results. But that's my intuition about it, that it will actually scale to high dimensions. Yeah.
Okay, I see. So in my understanding, on this part, there's no improvement over ENKF, right? It's about the same issue. It's the same.
Yeah, so
With
the
ENKF
state estimation
on that.
part I took from the ensemble Kalman filter. Of course, you could use another particle filter if you want. I mean, I used the Kalman filter here. The new part is really that the control on top of the Kalman filter, because Kalman filtering in weather prediction, there's no control. People just do quotation mark prediction, data assimilation, prediction, data assimilation, right? So the new thing is really the combination of control and filtering. Yeah.
Okay, thank you.
Yeah. So the new thing are these equations essentially, right?
Are there other questions? If not, then let's thank Sebastian and also Peter again for their very nice presentations.
Thank you, guys.
And before we go, I have a couple of announcements specifically to the participants at the trip to Alula. So basically, to summarize, please check the WhatsApp messages that you should all have received. In particular, please check out at the hotel tomorrow morning, if you're staying in the hotel, of course. There will be quite a number of people who want to check out at the same time, because we need to be at the bus at 6:30 in the morning. So please try to not time it at the last minute. We should really, if you want to coordinate with people, but I personally, I think I will aim for maybe 6 o'clock and rather than 6:30. You can leave your luggage there at the hotel if you want. If you say you only want to take a small bag with you to Alula, you can leave it there at the reception or at the left luggage facility. What else? Right, so this was about the, right. And then everybody should check in online for the flight. If you have not done so, please do it. If you have problems, please contact the travel agency as is detailed in the messages by someone. Right. And other than that, I am actually looking forward very much to this trip and to the excursion. And if you have questions, I would just suggest to, again, use the WhatsApp channel or talk to us. But in any case, all right. So thanks a lot and have a nice afternoon.